Hi everyone and welcome to the learning curve. In this video, I'll be looking at applications of the central limits theorem, one of the most famous theorem in applied mathematics and statistics, which is used specifically to calculate the probability of the sample mean among other applications. The central limits theorem is an extremely important part of everyday decision making. Imagine a world where you could predict the unpredictable. What if seemingly random events, when grouped together, always told the same story? Today we're diving into a mind-bending mathematical concept that explains why this phenomenon isn't just a coincidence, but a fundamental truth of the universe. Think about the last time you took an average, maybe an average commute time, or the average score on a test. What if I told you that regardless of how wild those individual times or scores were, if you took enough averages, they'd always start to look remarkably similar? We're about to explore the incredible principle that makes this happen, revealing the hidden patterns in randomness. The central limits theorem proposes that as you increase the sample size taken from a population, first of all, the mean of that sample, x bar, tends closer and closer towards the population mean mu. In particular, if the sample size taken from a population n is greater than or equal to 30, the sample size x bar will approximate to the population mean, sample mean x bar rather will approximate to the population mean mu. So that as you increase the size of a sample drawn from a population, the expected value of the sample mean x bar will approximate closer and closer to the population mean mu. And indeed, as I indicated, if you take enough samples from a population, the values from those samples, as far as the mean x bar is concerned, will start to look more and more similar. So the principles of the normal distribution are used to calculate probability for central limits theorem problems or scenarios. In particular, when the sample size is large, the distribution of the sample mean x bar becomes approximately normal. When we're calculating probability using for the central limits theorem, that is when we're calculating the probability of the sample mean x bar using the central limits theorem, we standardize using the z formula, z equal x bar minus mu divided by sigma upon the square root of n, where x bar is the sample mean for which we're calculating the probability, mu is the population mean, sigma is the population standard deviation, and n is the number of observations or sample size. In this question, we are told that the time taken by a randomly selected applicant for a mortgage to fill out a certain application form has a mean value of 10 minutes and a standard deviation of 4 minutes. If 40 individuals fill out a form on a given day, what is the probability that the sample mean time taken is, firstly, less than 10.5 minutes, and secondly, between 11 and 12.5 minutes? Let's get straight into it. Let's show you how the central limits theorem can be used to solve these problems and help managers, supervisors, businesses to make very important decisions. So let us write the probability statement for A. We are interested in the probability that x bar, the sample mean, will be less than 10.5 minutes. That is the probability that the time taken to complete a mortgage application will be less than 10.5 minutes. The average time will be less than 10.5 minutes. So to compute this probability, we're going to standardize using the indicated formula. So I'm going to re-express this as the probability that z, using z to replace x bar, and I keep the less than sign. Then I write the formula that we use to standardize x bar using the central limits theorem, which is x bar minus mu divided by sigma upon the square root of n. And this is how we can actually compute probabilities, the probability of x bar, as long as the primary conditions for the use of the central limits theorem are satisfied, which primarily is that the sample size drawn from a population is sufficiently large, that is n greater than or equal to 30. So going further with this, we get the probability that z is less than, now we're going to substitute based on the values that we're given. X bar is the value for which we're calculating the probability, which is 10.5. Mu is the population mean, and the population mean given to us in the question is 10 minutes. We know that this is the population mean because this is the average time that it takes to fill out mortgage applications overall. And so that's the population mean mu, which is 10. We are also given the population standard deviation of 4 minutes. So we're dividing all of this by 4 upon the square root of n, where n is equal to 40. So that this becomes the probability, when we simplify now here, this becomes the probability that z is less than 10.5 minus 10, which is 0.5. And when we divide 4 by root 40, we get 0.632. And now further, we just need to divide 0.5 by 0.632. So we get the probability that z is less than 0.79. So our standardized value is 0.79. Now at this stage, once you have standardized, it is recommended that you draw the standard normal curve to show the area of interest. That will help visualization purposes and help you to compute the correct probability. So we know the mean of the standard normal distribution is 0 in the center here. Then 0.79, which is positive 0.79, is going to be a value to the right of 0. So I just locate an arbitrary value here, an arbitrary point here. 0.79 is to the right of 0. Then we're going to shade the area to the right of it. The reason why we're shading the area to the right of it, we're going to shade the area to the left of it. And the reason why we're shading the area to the left of it is because this is a less than problem. See, it says the probability that z is less than and the probability that x bar is less than. We keep that less than sign right throughout. So we are shading the area to the left. If it was a greater than problem, we would have shaded the area to the right of 0.79. But since it's a less than problem, we're shading the area to the left of the standardized value, 0.79. So to get the probability of the area to the left of 0.79, all I need to do is to go to the standard normal table and go into the z column. I go down to 0.7 and then across on the 9. So 0.7 and then across on the 9, and the reading for that is 0.7852. This is a full table. So the answer here, which means that full table meaning that the total probability goes up to 1 roughly. So 0, we go down in this column, the z column, to 0.7 and then across on the 9, and the probability reading for that is 0.7852. So our answer here is 0.7852, or we could say 78.52%. So what this means now is that there's a 78.52 percentage chance that the average time taken to complete a mortgage will be less than 10.5 minutes. As you will appreciate, this can be very important in decision making and inform interventions that businesses need to make to improve operating efficiency. All right, so that's 0.7852, 7852, which is also 78.52%. Okay, so it's a fairly high probability that it will take less than 10.5 minutes for clients to complete a mortgage application form. Now let's look at B. In B, we're asked to find the probability that it will take a client between 11 and 12.5 minutes to complete an application form. So here I'm going to set this out as the probability. So this is my probability statement now. This is the probability that x bar is less than 12.5, which is the upper value in the interval that we're given, but greater than 11. Said another way, we could say this is the probability that x bar, which is the average time from the sample, is greater than 11, but less than the higher value of 12.5. So we need to standardize two values here. So we're going to rewrite this as the probability, and wherever each value is, the 11 and the 12.5, I'm just going to write the standardization formula for x bar. So this is x bar minus mu divided by sigma over the square root of n. Okay, and I'm going to say less than, wherever I see x bar, where I see x bar here, I'm going to replace it with z. So this is less than z, less than, and I'm going to write again x bar minus mu divided by sigma, the standard deviation, over the square root of n. And we're going to do our substitutions now. So the x bar values are the values for which we're calculating the probabilities, starting with the 11. So this will be 11 minus mu. Mu was given to us as 10, divided by sigma, which was also given to us as 4. And we know that the square root of 40 will be what we put here because n is 40. Less than z, keeping the signs. Less than, now we're going to insert the higher value of 12.5 here for x bar. And we're going to take away the mu value, which is the population mean given to us in the question of 10. And again, we're dividing by 4 upon the square root of 40. Close that bracket right there, place my probability sign, and this becomes the probability. Now let us simplify. This is going to be 1 divided by 0.632, because that's 10 minus 11 minus 10 there. 1 divided by 0.632. Then on the other side of the fence, this will be 2.5 divided by 0.632. There we have it, 10.5 divided by 0.632. I'll close that bracket and let us simplify further now. When we divide 1 by 0.632, so 1 divided by 0.632 is going to give us 1.58. So here I'm going to be interested in the probability associated with 1.58. And let's say for the upper value here of 2.5 divided by 0.632, that is going to give us 3.96 rounded to the second decimal place. So here I'm interested in the probability that z is greater than the standardized value of 1.58 but less than the standardized value of 3.96. We're going to draw our standard normal curve to visualize this result. So 0 will be in the center. Both 1.5 and 1.58 and 3.96 will be to the right of 0 because they are positive values. So I'll just sketch the marks here. It's a sketch, so you don't need to be extremely precise with where the values are located. Just make sure that it follows the appropriate numbering of the number line. So this is the error that I'm interested in, the error between 1.58 and 3.96. So to find this probability, what I'm going to do is to take the reading for the higher value. We're going to take the reading for the higher value of 3.96 from the table, and then we're going to take the reading for the lower value of 1.58 and subtract the results. So that's how we deal with these positive strips. When we have a positive strip like this, two positive values, and we're trying to find the probability of the error between them, using the full table, you take the probability for the higher value and subtract the probability for the lower value in the interval. So let's find 3.96. In this particular table, we do not have 3.96 represented. All right, because you realize that this particular table goes up to 3.4, but there are other standardized tables that will go up further. But if using a standardized table that goes up to a higher value than this one, the reading for 3.96 is 9, 9, so 4 nines and a 5. That's the reading associated with 3.96. But on this table, we can find the reading for 1.58. The principle is the same. So to find the reading for 1.58, we go down to 1.5 here, 1.5, and then we go across on the 0.08 here, 1.5, then across on the 0.08, and that is 0.9492. So that's 0.9492 right here, and 0.9492 is the reading for 1.58. So what we're going to do now is that we're going to subtract these values. So this is going to be 0.99995, take away 0.9492, and that's going to give us a pretty low probability here of 0.0575 rather. So a pretty small probability. So this is 0.05075, and as a percentage this would just be 5.075%. so there's a 5.075% chance that it will take between 11 minutes and 12.5 minutes to complete the application form for the mortgage. This is compared to the probability that it will take less than 10.5 minutes, which was a high 78.52%. So what these results together are saying is that it's unlikely that it will take a high amount of time, such as, for example, more than 10.5 minutes, certainly above 11 and 12.5. It's going to take, it's not going to be very likely that it will take that long to complete the form. In this particular case, again, the probability that the average time that it will take to complete the form for the mortgage application is between 11 and 12.5 minutes, is a pretty low 5.075%. So depending on what the standard is, in the population as a whole, it takes 10 minutes to complete a form on average. So anything beyond that seems to be a pretty low probability. So this kind of information can be extremely useful in making practical business decisions. So in this video, we've defined and explained and exemplified the application of the central limits theorem. There will be more follow-up videos on the use of the central limits theorem in generating predictions, estimating probabilities, and making sound business decisions. Thank you for your time. Remember to like, share, and subscribe as we continue our indulgence in the world of mathematics.